Good day to everyone. Today we are going to learn about sample injection system. The picture shows the schematic diagram of gas chromatography, which consists of the gas, syringe, which is auto-injector, injector or inlet, column, which is inside the oven, detector, and chromatogram. Sample injection is the most important step in GC instrumentation. Columns and detectors are not much use if there is no sample introduction. Well, injection is the entire process of transferring a liquid sample from a syringe through the inlet and into a column. Well, injector is the device which is auto-injector or human that performs the physical task of transferring the sample from a container into the GC. So class, let's move on to GC column. So packed column and capillary column. The difference is packed column contains a finely divided inner solid support coated with liquid stationary phase. Most packed columns are 1.5 to 10 meter in length and have the internal diameter of 2 to 4 millimeter. So this is the picture of packed capillary column class, cross section of the packed capillary column. While open capillary column is actually open tubular column, and capillary column are a tin fused silica, which is purified silica glass, and typically about 10 to 100 meter in length and 0.25 millimeter inner diameter, and has a stationary phase coated on the inner surface. So this is the picture of the capillary column. Fundamental problems with GC injection when dealing with packed column and capillary columns. So well, packed column is relatively simple because syringe needles easily fit within the bore of the tubing that commonly used with the packed column. Therefore, when using a syringe to inject into a packed column, the entire amount of sample that leaves the syringe enters the column. While capillary column, the internal diameter is smaller compared to the packed columns. Therefore, the syringe needle do not fit inside the column. So example class for the packed column, this will be the tubing. So now, a special interference between the syringe and the capillary column is needed, where sample will be evaporated and mixed with the carrier gas and transferred to the column, in this case class. So this is problem number 1. So fundamental problems with capillary injection. So if we compare with the packed column and the capillary column, there is a little chance of overloading the column with typically 1 microliter liquid injection in packed column compared to the capillary column, which contains only a few milligrams of stationary phase, meaning that 1 milligram injected sample has a mass very similar to the stationary phase mass, thus leading to the overloading. So this lead to the development of the split inlet, which significantly complicates the capillary system in GC. So class, the diagram shows the packed column and how the samples travel, and the eluted peak will be eluted at the certain retention time. The figure shows the overloaded peaks. So if the peaks is overload class, we will get a very broad peak, something like this, okay, in GC. Column overload. So basically, the overloading of the column happens because of less space in the column. So this means that to solve this overloading problem, we need a bigger space, okay. Okay class, let's move on to the capillary inlets. So capillary inlets, we have vaporization injector on column. Okay, vaporization injector can be divided into the splitless or program temperature vaporization. Okay, the diagram shows the basic vaporization injector, which consists of spectrum nut, spectrum, gas liner, and column. Basically, the spectrum isolates the sample flow part from the outside world. It must provide a barrier that is readily penetrated by the injector needle while maintaining the internal pressure without contaminating the analysis. So they are usually made of high temperature, low bleed silicone rubber formulation. Well, liners. Liners are centerpiece of the inlet system in which the samples is evaporated and brought into the gas phase. Many liners designs use deactivated glass wool packing. Usually, the glass wool will be in a center or held in a place near the center of the liner. The function of the liner is to provide the additional surface area for a complete volatilization of the sample to minimize the thermal discrimination. Trap non-volatile components and septum particles before they reach the column, and to wipe any samples from the syringe needle, thereby increasing the reproducibility and preventing the sample residue buildup at the septum. Okay class, let's move on to the basic of vaporization injector. The common misconception about the injector system is composition of the sample introduced into the column is identical to that of the sample before injection, and this assumption is false except in the case of direct on-column injection. Usually, the injector temperature should be hot enough to ensure the instant vaporization of the entire sample. Excessively high temperatures may cause degradations of thermally unstable compounds in the samples. Excessively low injector temperature may also cause incomplete or slow vaporization of the sample and may result in broad or tailing peaks, especially for high boiling point compounds. Therefore, a rapid transfer of the vaporized sample from the injector into the column is desirable in order to obtain highest efficiency. The diagram shows the difference between the narrow band and the wide band. So, short band and the long diffuse. Okay, solute bands, if let's say class, if short concentrated, so the separation will be nice. If let's say it's let's say 1000 runs in long diffuse for 20 minute, so solute bands is overlapping to each other, so you will get a very broad peak. So same column, same chromatography conditions. Some basic terms for injector. A liquid expands to many times of its original volume upon vaporization is considered as backflash. This often causes a momentary high pressure plus, which is greater than the carrier gas pressure in the injector. If the final pressure of the vaporized sample exceeds the injector liner volume, some of the vapors flow out of the liner. So the amount of the sample expansion depends on the sample volume, injector temperature, and the column head pressure. So class, where do the vapors go? Condense on any surface that is below their respective boiling points, such as septum and carrier gas line. The diagram shows the GC injector backflash. Sample expands to overfill the injector line and injection port. The more volatile a compound is, the more likely it to be susceptible to backflash. Usually the solvent is the most volatile component or as the solvent flashes out of the injector liner, it may carry other volatile sample component with it. The problems with backflash is losses of sample, baseline interference, ghost peaks, tailing or broadening. But how to minimize backflashing? Use larger volume of liner, small injection volume, low expansion solvent, lower injector temperature, high carrier gas flow rates, and high head pressure. Some basic terms for injector, which is discrimination. It is common for the entire sample not to be fully vaporized at the time of the introduction into the column. Vaporization is more rapid and more complete as the compound's volatility increases, because only the vaporized portion of the sample enter the column and a different percentage of each component actually enters the column to get separated. Thus, the percentage is greater for the more volatile components than for the less volatile components, and this effect is called as the injector discrimination. Example of the discrimination effects: for the equal amount of each component, the later eluting, which is less volatile component, show a progressive decrease in peak size as shown in this figure. So class, let's move on to the major factors that affecting the injector discrimination, which is the sweep time. Sweep time is the time it takes for the carrier gas to sweep the injector volume. The faster the sample is swept into the column, the less time that is allowed for the vaporization. Thus, the more volatile components have enough time to vaporize fully, whereas less volatile components are proportionally less vaporized. Mixing. Injector liner can be designed to mix the gaseous sample thoroughly prior to the introduction into the column. The more mixing, the less discrimination. Point number 3, differences in solute volatility. Components with boiling point differing by 200 to 300 degrees Celsius can exhibit tenfold differences in peak size. Okay class, let's move on to split or splitless injector. In split injector, it's designed to solve the above mentioned fundamental problems, which is syringe does not fit into the capillary column and overloading problems. It allows the introduction of the user selectable fraction of the injector sample into the capillary column by adjusting the relative flows of carrier gas into the column and to waste through the purge valve. The simplest technique for relatively concentrated ppm or higher samples. Usually, in split ratio, 1 over 80 of the injected sample will be introduced into the column. Higher split, smaller amount of sample on column. So the calculation here shows the split ratio calculation. Okay, let's move on. As for the splitless mode, it employs the same instrumentation as the split inlet, except that the purge valve is closed, transferring nearly the entire injected sample into the capillary column rather than venting most of it through the purge vent as split mode. Injection using the splitless inlet is the most common means for improving detection limits, and it's currently the most commonly used technique for trace, which is low ppm and ppb analyte concentration analysis. Okay class, let's move on to the capillary inlets on column is designed to allow the placement of entire sample directly into a capillary column without a separate vaporization chamber. This may require a special syringe with the needle outer diameter smaller than the internal diameter of the capillary column. The sample reaches the column as a liquid which is later vaporized by the temperature programming the column. Dirty samples may be problematic as nearly all the sample material reaches the column. May not be applicable for all the situation, but this technique is a choice for the best quantitative analysis. As for the program temperature vaporization inlet, it is modified split or splitless inlet that allow cold injection and rapid temperature programming. This design allows the inlet to perform a pre-separation of target analytes from other components of the sample. This procedure, similar to the on-column injection, the injection occurs while the inlet is cold and the injection is performed into the chamber like split or splitless inlet. This chamber is rapidly heated to dissolve the sample into the capillary column. Figure 1 shows the schematic representation of the PTV inlet, and the diagram also shows the difference between the liquid injection and the headspace. So class, selection of injector. It is more often driven by the availability on the instrumentation in the laboratory. Split and splitless inlets are far more common than on-column or PTV, so they are nearly always tried first. For example, chart for choosing an inlet based on sample type. For example, if the concentration is very high and the sample stability is unstable, analyte boiling point is high, solvent polarity is polar or non-polar, so the technique of choose can be on column PTV. So you may refer the rest of the example by referring to this table. In most cases, liquid and gaseous samples are introduced into the gas chromatography inlet using microsyringe, and as for the liquid samples, 0.1 to 10 microliter syringe, and for the gaseous sample the volumes are about 10 to 1000 microliters, and the syringe should be regularly checked for any leaks and should be replaced if there is a need. And the figure here shows the gas type syringe with Teflon tip plugger. So usually this type of syringe that we will use. Syringe filling technique. The best results are usually obtained when the syringe needle does not contain any sample, especially for lower injection speeds. When the needle is inserted into a hot injector, the needle is heated very rapidly. Volatile compounds in the needle, including the solvent, may begin to volatile and leave the needle before the syringe plugger is depressed. This introduces a small amount of sample into the column before the rest and creates a small peak immediately in front of each peak. So most needles on 10 microliter syringe have a volume of 0.8 to 1 microliter. If 1 microliter of liquid is measured in the syringe barrel, the actual volume is about 2 microliter, and a 2 microliter volume as measured in the syringe barrel is actually about 3 microliter, which is not double the measured 1 microliter volume. So example syringe filling technique for a manual injection. So the air trap here, sample in the solvent, and the air is here. So this example. Injection speed can be thought of as the speed of the plugger depression and insertion or withdrawal of the needle from the injector. The high carrier gas flow in the split injector rapidly sweeps the vaporized sample into the column. Therefore, the entire sample needs to be introduced into the injector very quickly within 1 to 3 seconds. Otherwise, it may cause slightly broad peaks, or sometimes it may cause some split peaks as well. As for the auto sampler, is primarily used to allow unattended sample injection. greater reproducibility of auto-sampler injection over manual injection. Injection speed and sample amounts are controlled very precisely, resulting in the peak size reproducibility superior to the manual injection, and it can be fast injection as well. The primary function of septum or septa is to seal the injector, thus preventing vaporized sample and carrier gas from leaving and air from entering the injector at the point of syringe introduction. Since a syringe needle repeatedly punctures the septum, it has to be periodically changed to prevent the leaks. A septum leak may result in retention times and peak size variation, which may makes the analysis more difficult and inaccurate. A more serious in the leakage of air into the injector, which exposes the column to high concentration of oxygen. So thus, oxygen will accelerate the degradations of the stationary phase, resulting in high column bleed and activity, and finally will lead to the short column life. Okay, class. So I have given the examples of the peak, the normal peak and the problematic peak due to the possible causes. Okay, it can be from the septum bleed or large leak at the septum or carrier gas leak at the septum. Okay, the difference between the normal peak and the problematic peak and how to overcome this. So class, this figure shows the septum bleed chromatogram, and the typically mass spectrum of the septum bleed looks similar to the column bleed as well. Okay class, why we must replace liner? The following problems will occur if the liner is not changed on the regular basis. Peak size reduced, solute discrimination, poor reproducibility, sample decomposition and ghost peak. So usually we will change the liner based on the previous pattern, peak shape or retention time, peak discrimination and poor reproducibility. And when and the liner selection, you main concentration is volume. So larger volume liner, which is more than 800 microliter, are characterized by larger inside diameter and typically used with the injection size of 1 microliter or more. The small volume liners with small ID are usually used with injection volume less than 1 microliter. So class, here you can see the matrix contamination and septum contamination on the glass liner. So glass liner is usually untreated glass, contains silanol groups that interacts with most compounds. This silanol contributes to pigtailing or adsorption problems for active compounds. Therefore, silation converts the silanols to groups that do not interact with active compounds. Most of the commercially available liners are deactivated or silated. However, liners may slowly lose their deactivation and eventually may not be suitable for use with active solutes. A cleaning will not restore these liners to their previous level of inertness. So class, here glass liner silation. So the silation procedure, usually we will place the liner in a screw cap test tube, cover the liner with 10% of trimethyl chlorosilane, tightly seal the test tube with Teflon lined cap. Let stand for about at least 8 hours. Then remove the liner from the solution and rinse thoroughly with the toluene, then methanol. Dry the liner at 75 to 100 degrees Celsius. So how to troubleshoot the liner? So usually when we have a tailing peak, leading peak, or baseline rise before the after peak. Okay, is the possible cause, it can be due to the sample decomposing, or it can be sample component adsorbed by the column, inlet liner, or contaminated the gold inlet seal. So needle heating and breaking packing in the inlet liner, column and polycut sample absorption, broken or chipped inlet liner. So the remedy is here. Remedy is how to overcome this problem. So you may refer to all these remedy class. So class, this is another example. So with that, thank you so much.